Does anybody have any questions before we start? The answer key for the exam's on YouTube. You should be able to watch it. Come ask me questions during office hours if you'd like. And for those of you that are starting to come in, please log on to Socrative and take the quiz. This was the first question after me asking you to enter your student ID numbers, which of course is not a question I'm going to grade anybody on. So what's the allele, calculating what's the allele frequency of A? We have lots and lots and lots of different types of answers, so it's a good thing that you're here so we can clear up calculating allele frequencies. So if you have a big A and a little a, then you have given genotypes. How do you calculate allele frequencies from that? The answers are diverse, which is good for an evolution class. So if you want to calculate the allele frequency of little a, what do we do?
Just add all the little a's together.
Okay, so we're going to add, yeah. So what genotypes have little a's?
Heterozygote and homozygote.
Yeah, the heterozygotes and the homozygotes have little a's. So we've got 3 heterozygotes. They each carry 1 little a, so that's 3. And we've got 10 homozygotes, so how many little a alleles is that? Right, it's 20 because each of those 10 individuals carries 2 little a genes. So that's 23 little a's. And then how many total individuals do we have? How many total alleles did we look at? No, how many individuals, how many organisms did we look at? We've got 20 individuals, 20 organisms, each of whom have 2 alleles. So you've got 40 total alleles. So you've got 23 over 40, whatever that fraction happens to be.
I think it's just 23 over 40.
Yes, I don't think we can reduce that any further. So we call it 23/40ths. Or 57.5% if you want to use your calculator. So the allele frequency of little a is 0.575. 57.5% of the alleles in the population are little a's. Okay. So that was the first question. Any questions about that? Just tallying how many little a's. And that's why it's important for me to tell you in this question, which we usually will be, that we're dealing with diploid individuals. Because if I don't tell you how many alleles every individual is going to have, you don't know how many alleles there are in the population you're looking at. Okay. So moving to the next question then. So you've got, I give you allele frequencies. Big Q and little q are 0.1 and 0.9. So if this population's in Hardy-Weinberg equilibrium, if you know the allele frequencies, how many big Q over big Q genotypes should we expect? Right there. So let's see responses. No, they're small. Good. 1%, 9%, 1%, 10%, 75%, 40%, 20%, 10%. So how do you go about solving this problem? It's clear that the class doesn't have a consensus. So what's the Hardy-Weinberg formula?
Q squared plus 2pq plus d squared to make it, yeah, equals 1.
Okay. We talked about this at the end of last class, so this is not supposed to be a refresher. This is the first time we've actually been applying Hardy-Weinberg equilibrium to questions. So I'm trying to preview some of the things that you would actually use the Hardy-Weinberg equilibrium to do. Which genotypes do these correspond to? So Q square is a frequency. Which genotype? So little q, I didn't tell you. You're free to choose. So let's say that little q is, maybe I should have used different gene terminology. Maybe that was what was confusing. Big Q and little q. I just chose those because they're easy letters to distinguish from each other, capital and lowercase form. If you were crossing individuals that had big Qs and little q's, and you wanted to predict how many genotypes there are going to be in the next generation, what would you do? What sort of process do you go through? What do we draw when we're going to predict genotypes of a next generation?
Punnett square.
Punnett square. So what does a Punnett square for this problem look like? If you've got allele frequencies of 0.1 and 0.9, what percentage of the gametes are going to carry big Q? 1%. Or 10, yeah, 10%, 0.1. Right, so that's this part right here. Big Q is a frequency of 0.1 in the population. And little q is at a population or at a frequency of 0.9. So if we represent the frequencies of the gametes, little q occupies a tenth of the gametes. So a tenth of the width of the total Punnett square. And the little q, 90% of the width. And if this happens to be a randomly breeding population and it meets all the other assumptions we talked about last class, then what you're basically doing is you're asking if you make random combinations of the gametes that are in the population, where 10% of the gametes carry a big Q and 90% of the gametes carry a little q, that's all the information that was provided, basically.
Wouldn't you do like, wouldn't the frequency be like every single, the allele frequency, wouldn't you just multiply it by itself?
To find, yeah, what's the question?
The homozygous of big Q.
Exactly. So to find the area that occupies that square, the big Q over big Q homozygotes, that's the question. So how do you figure out the area of that part of the Punnett square? You multiply height by width, Q times Q. So in this case, Q squared, well, big Q, 0.1 times 0.1 is 0.01. So 1% of the area of the Punnett square. So that's the number of individuals that should have the little q over or big Q over big Q genotype. So what does this mean?
Does this mean that most of the genotypes are going to be small q?
Small q what? Yes, you're on the right track. So most of the genotypes are going to be the genotypes that occupy the bulk of this Punnett square, which are the individuals that inherit a little q from both parents. So that's 0.9 times 0.9 or 0.81. 81% of the individuals you'd predict to have the little q over little q genotype. So if you know allele frequencies, this is summary, if you know the allele frequencies, you can use Mendel's laws, a Punnett square, which is how the Hardy-Weinberg formula is derived, to figure out what frequency of genotypes you would expect. So that's going from allele frequency to genotype frequency. So if you know allele frequencies, you can predict what you'd expect to see in genotypes. Can you go the other direction? If I tell you a number of genotypes, can you calculate the allele frequencies? That's what we did in the first question. So you should be able to go back and forth. If I give you allele frequencies, or if you measure allele frequencies, you can predict what sort of genotypes you would see if you went out into the population and grabbed a bunch of individuals and genotyped them. And if you get genotype information, then you can figure out, just by tallying essentially, what are the allele frequencies in the population. So if a population's in Hardy-Weinberg equilibrium, which of these various things are true? Allele frequencies aren't changing, two alleles are at the same frequency. Let's check your answers first. So we've got A, allele frequencies are not changing, about 50%. That's true, so A is a correct answer. And so is C, natural selection is not acting on the alleles. That's the interpretation of what we discover when we find a population isn't in Hardy-Weinberg equilibrium. That suggests that natural selection isn't acting. If natural selection was actively selecting for or against an allele, its frequency would be changing. It would either be selected for, it would go up in frequency, selected against, it would reduce in frequency. That's when we would observe that Hardy-Weinberg equilibrium is not met. It's very likely that some of you have questions about the other optional answers. So now's a good time if you want clarification. Why B and D aren't the correct answers.
What was C again?
So C, natural selection is not acting on the alleles. So when a population's in Hardy-Weinberg equilibrium, then natural selection isn't acting on the alleles. And the opposite is also true. When allele frequencies are changing, that suggests the possibility of what things? Either natural selection or what other forces cause allele frequency changes? Mutation, drift, migration, immigration and emigration, population size change, drift, and non-random mating. All stuff from last class. So quick review. There are a lot of forces that can cause population frequencies or allele frequencies to change. Therefore, if they're not changing, if allele frequencies are staying the same, it's likely true that all of those conditions are true. That there is random mating, there is no migration, there is no mutation that's causing new alleles to arise, and also that natural selection is not actively acting to change an allele frequency. I wanted to go over this because of the midterm. And I totally admit I was mean when I wrote this question. It's true. I was trying to see who was bold enough to go against the grain and to not choose one of the two answers I suggested might be the answers. So in this phylogeny, new phylogeny we've never seen before, so who's a closer relative to a sunfish? The bear or the chimpanzee? So they're sister taxa, they share the same common ancestor. So the evolutionary distance between this individual from which all three of those species were derived back in time, the distance is the same between the sunfish and either of those two species I'm asking about, bears and chimpanzees. Total branch length from tip to tip, sunfish to bear or sunfish to chimpanzee is the same. So they're equally related. On the other hand, what's true about the second question? When you focus on a lizard, who's more closely related, the newt or the bear to the lizard? So you go back to the lizard branch to find a common ancestor. So you go least far back in time to find the common ancestor of the lizard and the bear. You have to go farther back in time to find the common ancestor of the lizard and the newt. So who's more closely related? Lizard and the bear. They derived more recently in time from a common ancestor here. The newt's more distantly related. You have to go farther back in time to find the individual that gave the individual population that gave rise to both the newt lineage and the lizard lineage. So you go back least far in time from the lizard to find the common ancestor of it and a bear. So lizard and bear are more closely related. Lizard and a newt, you have to go farther back in time to find the common ancestor, so they're more distantly related.
Okay, but the bear and lizard, they don't even have a common ancestor together.
They do. Both of those lineages derived from that individual. So it might help, for example, if we do that. Forget primates. So now lizard and bear look like sister taxa. Okay, they're more closely related. Yeah.
This is just based on distance, right? The branch lengths?
So in this case, the branch lengths aren't distance related. So this is a form of a phylogeny that's just representing the relative distances. So it's not absolute distance, it's relative distance. So shorter branches do mean fewer changes, more similarity, but they're not proportional to each other. Thank you for the questions. More? Any questions at this point?
Wait, so you said which one was more related?
So we already did this summary. We talked about the forces that change allele frequencies and what Hardy-Weinberg equilibrium means. Ooh, and we already talked about this too. The Hardy-Weinberg formula. Covered this at the very start of class when we talked about the answer to the first quiz question. By the way, those of you that have come in subsequently, if you want to record your presence here, go to Socrative and work on the quiz. I'll leave it open until about 10. So you've got time after class to work on it so you can focus on what we're doing now. Okay. One last sort of review point. We've never had the opportunity to use the chi-square formula to figure out whether or not a population's in Hardy-Weinberg equilibrium. Let's keep it that way. Uh-oh. I'm getting blowback on the chi-square analysis thing. It's like, yeah, it's the two things that you want to hear least about, Punnett squares and Hardy-Weinberg equilibrium. But they're related. Yes, they are. So we have to do exactly the same thing here as in the quiz at the start. So we're going to figure out whether or not natural selection's happening at this gene, the E gene. And we have a population of flowers, we've genotyped them. So now's your chance to practice again, changing genotype to phenotype. So what are the allele frequencies? It's always the first step. We've got a big E and we've got a little e. But what are the frequencies? So E over E, we've got 14 times 2, 14 homozygotes, each of which have 2 alleles. And then we add to that 10 individuals, each of which have 1 little e. So you can think of the 2, and you can think of that as 10 times 1 if you want. The number of big E alleles in the genotype. So 28, 38. Good, I'm getting affirmation from the front row. What about little e's?
34.
So it's 12 times 2, the number of homozygous individuals, each of which have 2 little e's, plus the same, plus the 10 heterozygotes. So 34. Okay. And how many total alleles? 72, 36 times 2. So 72 total alleles. So we got 38 out of 72 biggies and 34 out of 72 little e's. So hopefully 38 and 34 add up to 72. Good. Okay, is natural selection acting? So what do you do next? If you calculate the allele frequencies, how are we going to know if the population's in Hardy-Weinberg equilibrium? Keep in mind that we're about to talk about the chi-square test. So what are these things that I'm circling here in red? These are haplotypes, these are frequencies, these are genotypes, right? So these are observed genotypes. What do we need to know whether or not the population's in Hardy-Weinberg equilibrium? If we're going to do a chi-square test, we need observed values and we need expected values. So how do we calculate the genotypes we expect? So we want to use the Hardy-Weinberg equilibrium formula. We've got allele frequencies. So what are the expected frequencies of E over E? So expected. Big E over big E, big E over little e over little e. What next? So we've got expected expected genotype frequencies. How do we calculate these? We don't actually have to calculate them right now, but what's the formula? So do you want big E to be P or do you want big E to be Q? Okay. So little e will be Q. So the frequency of those two alleles, 38 over 72 is P. So the frequency of the homozygous biggies is P squared. 38 72nd times itself. And then we've got 2 times 38 72nds times 34 72nds, 2pq. And EE is little q squared. I'll give you the answer. And I expect you to work through it after class. And if you identify any issues with doing this calculation, come talk to me. But when you do that, the chi-square value you wind up with, the number, is 7.15. So what? You do this chi-square formula, you total those 3 clauses together, you get a value that says 7.15. What does this mean? How do we interpret it?
We have to get the degree of freedom.
Right, so that number 7.15 corresponds to the bulk of the chi-square table, the chi-square test statistic values. So, yeah? Degrees of freedom. So we've got that 7.15 we find here. We need to figure out which row of the table we're looking at. How many degrees of freedom? Which is the number of categories minus 1. So we've got 3 different genotypes. We subtract 1, and that gives us 2 degrees of freedom. So you read across from degrees of freedom is 2 until you hit your magic number, 7.15, which is where? Somewhere in here, between 5.991 and 7.37. What's the p-value? That's the goal. Probability. So once you find where that number lies, you look up and find what p-values there, the subscripts next to the chi-squares. What numbers, what p-values that chi-square value, 7.15, is associated with. Somewhere in between 0.05 and 0.025. So that's the process of the interpretation. Find the chi-square value by the calculation, observed minus expected squared over expected. Calculate the number of degrees of freedom, find where they meet on this table, and then you look up into the header of the columns to find out which p-values are on either side of the number your chi-square value. The most important thing is, what does it mean? The question is the population in Hardy-Weinberg equilibrium? The answer? So what does it mean when a p-value is less than 0.05? So this is, for me, when I was a U, this was the problem. I could, like, plug and chug, sure. It's significantly similar or significantly different? That was the thing I always had. So yeah, it's significant. That doesn't tell me anything. So scientists have agreed that when p is less than 0.05, the observed and the expected values are significantly different. That is, the observed values are not equal to the expected values. So that's something you just have to remember. When the p-value is really small, then the observed and the expected values are different. So we had genotypes that were observed of 14, 10, and 12, and we had expected values that were 10, 18, and 8. We expected 10, 18, and 8. We saw 14, 10, and 12. Pretend like you're staring at one of those maps with all the dots on it. You cross your eyes a little bit and you see the 3D image emerge. When you stare at the observed and the expected columns, could you explain, just in normal language, what's different between the two? Why is the observed different significantly than the expected? What happened? Who do we have too many of? Who do we have not enough of? So we've observed not enough heterozygotes. So we expected to see more heterozygotes than we actually saw. Oh, stop shaking the building. By contrast, if you have more of one type of genotype, then what's true about the other two? We have fewer, well, it's not necessarily true. So we observed 12, so we observed more homozygotes than we expected. So we have extra homozygotes and we have fewer heterozygotes. This population is not in Hardy-Weinberg equilibrium, observed not equal expected. We expected Hardy-Weinberg equilibrium. Small p-value tells us that this population is not meeting our expectation. Observed not equals expected. If you wanted to, could you tell a story about what might be happening genetically out in the environment? Seriously, tell the people upstairs to stop jumping up and down. If anyone feels sick, you feel free to go to the bathroom. Why might we see fewer heterozygotes than we expect?
Selection.
So it could be selection. What would natural selection be doing to heterozygotes? Selecting against them. So is it possible, when you see a population that's not at Hardy-Weinberg equilibrium, p is very small, observed is not equal to expected, one hypothesis that you might test is there something unfit about heterozygotes? There's something bad about being big E over little e. When you have that particular genotype, you're more often killed by a predator, or you're more often less likely to reproduce. So what's happening to those heterozygotes that's making them appear to be selected against? Or on the other hand, what's happening to the homozygotes that make them appear to be being selected for? Two sides of the same coin. So detecting Hardy-Weinberg equilibrium in a population is basically one of the first steps for evolutionary geneticists. If we want to study evolution, we have to find a population that's undergoing evolution. So we just go out and look for, is the population in Hardy-Weinberg equilibrium? When it's not, that's the first step. Then we start formulating hypotheses. Okay, what might be happening to cause natural selection in the population? And of course, this assumes that we've controlled for mutation, migration, drift, random mating, and so forth. Any questions at this point? Concerns, comments? So that you don't have to do those calculations for yourselves, I've got them right here. So the big E over big E, 27.9%. Big E over little e, 49.8%. Little e over little e. What sort of ratio does this look like? It looks kind of like, it's almost like a 1 to 2 to 1 ratio. And we see that when allele frequencies are almost equal. When P equals Q, or when the number of big E's is the same as the number of little e's. That should be familiar because that's what happens when you have a cross between two heterozygous individuals. You get that 1 to 2 to 1 ratio, homozygotes to heterozygotes to homozygotes. So that's kind of what this looks like. Allele frequencies, the big E is about 50%, the little e is about 50%. A little bit different. So this is what we expect. We expect to see 27.9% big E over big E, 49.8, and 22.4. We can't do the chi-square test. I apologize. We can't do the chi-square test yet. Why not? So we have expected values. Here are the observed values of these genotypes. So if we want to set up the chi-square formula, observed minus expected squared over expected, what do we need? What do we plug in this E column? 27.9%, 49.8%, and 22.4%?
49.8 divided by 2.
So what do we have to, so these are frequencies that we've calculated here in the upper left. These are expected frequencies. We have to convert that to actual individuals, numbers of individuals. If we went into the population, we picked a bunch of individuals, how many would we expect to have those genotypes? So 27.9% of how many individuals? How many individuals did we look at?
72.
Half that. 36 individuals. So our expected column had better add up to the same number. So if this population is in Hardy-Weinberg equilibrium, then the sum of those three genotypes should total the same number of individuals. So we need 27.9% of 36 times 36. And we need 49.8% of 36. And we need 22.4% times 36. Okay. So I calculated those to be, let's see, 10, 17.94, and 8. Should I round something? Maybe let's make that 18. So 10 plus 18 plus 8, 36. So that's how many expected individuals we would hope to see if the population's in Hardy-Weinberg equilibrium. We've got 3 different categories. We've got homozygous big E, homozygous little e, and heterozygotes. So what are we going to do next? Solve the equation. Perfect, we can plug and chug. How many times do we have to do this chi-squared formula?
3.
Same number of times as we have categories of individuals we're looking at. So we've got homozygous big E, we have to do observed minus expected squared over expected. We've got the heterozygotes, and we've got the homozygous little e over little e. So we'll practice this more next class. I want to make sure that we get to the point of actually interpreting the p-value. So you've all done this before in various classes. So you calculate observed minus expected squared over expected 3 times. So we talked about this concept last class. Just if you see an allele frequency changing does not necessarily mean you can conclude that natural selection is happening, that the new allele is either dominant or recessive, or whether or not it's beneficial or detrimental. Allele frequencies can change for a lot of reasons. You have to use the Hardy-Weinberg equilibrium formula and a chi-square test to determine whether or not allele frequencies are changing. So that's the Hardy-Weinberg equilibrium. It's basically the null hypothesis, the expectation of evolutionary genetics. How many genotypes would we expect to see? What does this all have to do with having short fingers and toes? Right, I started last class talking about Mendel's P's and this idea that if you've got a dominant trait, you expect after 2 generations, 3/4 of the population to have yellow peas. Brachydactyly is a dominant trait, so why after 2 generations do we not see 3/4 of all humans having this dominant trait? Why isn't it more common? Because it's, okay, so it's either rare or it's detrimental or both.
Could it be selected against?
How would it be, could it be selected against? How would it be selected against?
Not mating with the person with brachydactyly.
Right, so if, yeah, let's be honest. Small fingers has been in the news a lot recently. Sorry, I don't usually let politics intervene in evolution, but there you go. But it's totally, so yeah, it could be the case that brachydactylous individuals happen to mate with brachydactylous individuals more frequently than with non-brachydactylous individuals. So there could be, that's non-random mating. If you're more likely, if people of short stature are more likely to marry people of short stature, etc., that's non-random mating. That changes allele frequencies. It's also more likely because this is rare. So if 1 in 10,000 individuals in the world has the gene, that, regardless of whether or not it's dominant, sure, in a family that has somebody who's, let's say, capital B is the dominant brachydactyly gene, and they're heterozygous, let's say. If that person mates with and has kids with somebody who's, wild type, 2 little b genes, so not brachydactylous, what frequency of brachydactyly do you see in their offspring? 50%. Yeah, so every time you get a big B, you get a brachydactylous individual, and every time you have 2 little b's, you've got a wild type normal individual. I use normal lovingly. Right, so the allele frequency in this population, the population of this family, hasn't changed. You've gone from half of the parents having brachydactyly to half of the kids having brachydactyly. No allele frequency change, no genotype frequency change. So yes, in families that have the genotype that causes brachydactyly, if two brachydactylous people marry, like in Mendel's P cross up here, if you cross two heterozygous brachydactylous P's together, you would in the next generation expect 3/4 of their kids to be brachydactylous. That's just one family of the human population. If the frequency of big B is 0.01, and the frequency of little b, the wild type so-called allele, is at a 99% frequency, how many brachydactylous individuals do you expect in the next generation? You could plug this into the Hardy-Weinberg formula and find that you don't expect an increase in the frequency of the trait. It stays the same. Because 99% of the population is mating and having normal 100% non-brachydactylous kids at the same rate in every generation as the individuals that have that really rare trait, mating and producing more individuals with that dominant trait. So rare alleles stay rare. That's one of the predictions of Hardy-Weinberg equilibrium. Okay. So what we're going to talk about next class, sorry, it should say next goal. We're not quite there yet, of course, but we're going to get into a little bit of introduction about what we're going to talk about next class. Quantifying selection. So far we've talked about, yeah, a gene might be selected for or against, or an allele might be selected for or against. But we've been using very qualitative terms. It's beneficial, it's detrimental. Now we're going to start talking about how we actually put a number on how selected an allele is. Strongly selected, what value, what numerical value does it have? Is it weakly selected? Is it selected for or selected against? So this is from your textbook. Hopefully this is going to look familiar. You've done the reading already. In which of these situations are individuals going to be less fit? We've got two different mouse coat colors on two different environments. So top right is going to be more fit or less fit. You compare these two. Yeah, we're going to. So how do you predict fitness will be affected by having different coat colors on different background environments? So it's basically, yeah, this is a question about the concept is camouflage. So if the individual here, if their population evolved a light coat color because they're more fit on light colored backgrounds, then if you plop a dark colored mouse in there, or if a new mutation arises that causes the coat color to change, more likely to be killed by predators maybe, or somehow less fit in the environment. And you might expect the same thing for a light colored mouse on a dark environment. So how do we measure fitness? There are many ways. What's one way you can measure fitness? So you can count the number of offspring. That's the go-to for evolutionary biologists. In this case, we take a slightly different tact, which tries to approximate the same idea. It's just easier in the field not to count how many offspring these mice have. Kind of difficult. Some people do it, but it's a lot of field work. So in this case, you just measure, say, lethality. So how frequently are you killed if you're a light-colored mouse on a dark background? Of course, you can only die once. You understand. How frequently are mice with light coat colors killed on dark backgrounds versus what? Compared to? Yeah, compared to dark on dark background. So fitness, when we talk about fitness, it's always, or almost always, relative fitness. It's compared to something. Compared to what we deem, being so grand and human, what we deem to be the most fit phenotype in the environment, how relatively unfit is a different phenotype. And the value that we use to do this is called the selection coefficient, or S. So we're going to walk quickly through how to calculate a selection coefficient, and then we'll be done for the day. So in this environment, we've got a dark background. We want to know what's the selection coefficient for the allele that causes light coat color. So what is S for that combination? You've got a light coat color, you're in a dark background. So we set the dark colored mouse, we artificially, or by convention, say it's got a fitness of 1. So we predict in advance that the dark colored mouse in the dark background will have 100% relative fitness. It's the most fit trait. And if we have an S value of 0, that means that there's no selection acting on that gene. So S can range between 0 and 1. A selection coefficient value of 0 means it doesn't matter what allele you have. What does it mean if you have an S of 1? 100% reduction? It's 100% reduction in fitness. So selection values range from 0 to 1. And if you happen to get a 1, that's really bad for you. So S equals 1 means 100% reduction in fitness. So if you have this allele, you will die or not reproduce, at least. So that would be really bad. So we don't often see genes, you might predict, we don't often see alleles that have an S value of 1. In most traits that we study, the S values are usually really small, 0.1, 0.2, 0.5 for an individual trait. So as populations that would evolve ourselves, humans, we like to avoid S values that are big. So the last thing to do for today, here's one example of how to calculate, for example, a second allele that's recessive. So we've got one allele, allele 1, which causes a dark coat color on a dark background. A new allele, allele 2, causes a light coat. So we want to know what's the selection coefficient of having a light coat on a dark lava field, let's say. So we define that all of the individuals that have dark coats are going to have a relative fitness of 1. They're going to be the most fit because their coat color matches the background. But notice, did any of them die?
Yes.
So we started with 100 mice of 2 different genotypes, but we lost 10 between when we put all the mice on the lava field and when we came back and tried to find them. Well, this is true. This is what happens in nature because individuals, regardless of whether or not your coat matches your background, you still might die for various reasons. So this controls for the fact that lethality happens. You get predated upon even when you do have the right coat color on the right background. So the most fit population has a relative fitness of 1, but its survival probability is the ratio of 90 to 100, or 90%. So the survival probability, little p, of the best fit population is 90%. If you're optimal, your best chance is 9 out of 10 that you don't die. So then you look at the light trait, and you have much more lethality. We've got lost, 40 mice over the same time period. So it seems like having a light coat's much worse than having a dark coat. This is how we quantify that. This 2/3 value, the relative fitness, so how fit is dark coat or light coat relative to dark coat, relative to, implies what sort of calculation? Addition, subtraction, multiplication, division.
1 minus 0.6.
So we actually, it's ratio. It's a ratio.
So it's like fractions.
Yeah. So you divide the survival probability if you've got a light coat on dark rocks by the ratio of lethality, the probability of survival of the dark coat on the dark rocks. So 0.6 divided by this value, 0.9. And that's how you arrive at the relative fitness. So if you've got a light coat on a dark background, your you have 2/3 the fitness of a dark coat on a dark background, and it's the difference between 1 minus the relative fitness, as you saw on the previous screen, that leads you to calculate the actual selection coefficient, 0.33. So for next class, try calculating this exact same thing just for practice, because we went through that relatively quickly, on this bottom row, the third allele, allele 3, that causes a medium coat color, so somewhere between light and dark. Some point before next class, go to the todaysweek.com website, Biology 105, and just enter the number that you calculate for the selection coefficient for allele 3. Okay. When we come back next time, we'll keep talking about selection.